In section 6.1, we'll be discussing more about areas. So we're going to find areas between curves. Now, if we want to consider this region here S, it lies between two curves. The curve above it is y equals f of x. The curve below it is y equals g of x. And it's in between the vertical lines x is equal to a and x is equal to b, where those two functions f and g are continuous functions, and that the function above here is greater than or equal to the function below, meaning f of x is greater than or equal to g of x, for all x that's in between a and b. So just as we did for areas under curves in section 5.1, we're going to divide this surface area into n strips of equal width, and then we approximate the ith strip by a rectangle with a base delta x and a height f of x subscript I minus g x subscript I. Now if we look at this figure here, we could take all of the sample points to be the right endpoints, and we're going to create a Riemann sum. So if you take a look at this particular rectangle that we cut out from that surface, okay, you can see that f of x subscript I asterisk is above the x-axis. Below the x-axis is from here to here represents the negative part of the area of g of x subscript I with an asterisk. Now if we take a look at the entire distance, we would subtract those two because this one's negative to find out what that would be. So therefore that would be that distance. And then the width here is delta x. So this is your typical rectangle. Now what you would do is you would then create multiple rectangles to approximate what that area would be for S. So the Riemann sum would go as the following. So you're taking the area, right, of one rectangle, but you have more than one rectangle, which is the reason why you have the asterisks. So the Riemann sum, which goes from I is equal to 1 to n, of f of x subscript I minus g of x subscript I, multiplied by your length here, which is delta x. And therefore, that is the approximation to what we intuitively think of as the area of S. Now, this approximation appears to become better and better as n approaches infinity, meaning that the more rectangles that we get, the closer that we get to that approximation. Therefore, we define the area A of the region S as the limiting value of the sum of the areas of these approximating rectangles. So there is our first definition. Now, we recognize that the limit in definition number 1 is the definite integral of f minus g. So therefore, we have the following formula for the area. So the area for definition number 2 is equal to the integral that goes from a lower limit of a to b of function f of x minus g of x times dx. Now notice that if we have a special case to where g of x is equal to 0, the surface area is the region under the graph of f, and our general definition of the area reduces to our previous definition. So in this case, where both f and g are positive, you can see from this figure why definition 2 is true. So here we have an area under the curve y equals f of x minus the area under the curve g of x. So again, this curve is still above now the x-axis, but g of x is here and there is f of x. So we can still subtract to get the approximation of that area of S.